Hey physics friends, and welcome to 22.6, which is entitled the kilowatt hour. We're going to talk today about what the kilowatt hour is and a few other devices that we have around our houses that deal specifically with electricity, such as a fuse, a circuit breaker, a ground fault circuit interrupter, and an arc fault circuit breaker. So just a couple things that you might see around your house that are electrically related. How are they similar? How are they different? Let's get started. The kilowatt hour. The kilowatt hour, on its surface, it seems like a unit of power because it says the word kilowatt, but it's actually a unit of energy. And let me show you what I mean. Like a kilowatt could also be, you could just, a watt. What if it was a watt second? Right? A watt second is kind of like a kilowatt hour. It's just a watt in an hour instead of it's a second. And if you remember, a watt is a joule per second. And you multiply that by seconds. Joules per second actually ends up being a joule. A kilowatt hour is actually equal to a certain number of joules. How many? I can kind of show you. So one kilowatt hour. In 1 kilowatt, there's 1,000 watts. And 1 watt is equal to 1 joule per second. And 1 hour is equal to 3,600 seconds. Now, check this out. Look at all the things that are canceling out here. The hour has canceled. The kilowatt has canceled. This watt has canceled that watt. And then finally, this second has canceled that second. So you're left with joules. 1 kilowatt hour is equal to 3,600,000 joules. And it turns out that that's what the power company sells us. And currently right now, where I am in the country at this day, I looked it up, that residents where I live pay 12.6 cents per kilowatt hour. If you're a resident. Residential people pay 12.6 cents per kilowatt hour. And that varies. It's cheaper at night than in the day because it's the more demand during the day, so I have to create more of it, so they just charge people more. It's cheaper at night. If you have an electric car, you can actually program it to charge itself at night where you're paying less. If you're an industry, a farmer, it's 10.4 cents per kilowatt hour. So the kilowatt hour, what it is, it's a unit that the power company sells us. A unit of power that the power company sells us. And you see that I put power in quotations because they're not selling us power, they're actually selling us energy. So I've got an example question down here where you've got a pair of wireless headphones. Like the headphones that I have at home, they take a AAA battery, and I just made up a couple of numbers. I know that every AAA battery puts out 1.5 volts, and I'm just making a wild guess that it consumes this many milliamps of current. And this is roughly the cost of one battery, and it runs for 100 hours. How much am I paying per kilowatt hour? Let's figure that out. So these problems, at their core, they are what's called a dimensional analysis problem. I'm looking for dollars per kilowatt hour. So I have here dollars. $1.89. I'm going to put that in the top because I'm looking for dollars. I want that to be in the numerator. Kilowatts. The problem doesn't really tell me kilowatts, but you know what it does tell me? It definitely tells me hours. So these problems, there's no equation that go with problems like this. It's a dimensional analysis problem. I want to put things that I'm looking for right now. So I've got dollars on the top. I've got hours on the bottom. And now I have to figure out kilowatts. And this is kind of tricky. We're looking for kilowatts. The problem doesn't come right out and tell me the kilowatts like it did everything else. But you know what it does tell me? It tells me this stuff right here. I can use voltage and current to find how many watts, right? That power is equal to current times voltage. Now be careful. My current is listed in milliamps here. So 0.042 times my voltage of 1.5. That equals 0.063 watts. Now, I want to make sure I have kilowatts, so I can't just go plugging 0.063 into that. I need to change it into kilowatts, and I got to add 3 more zeros. 0.00063. That very low power these are. Now, I pull out my calculator, and I take this number, divided by 100, divided by 0.00063, and I've already done it. It turns out to be 300. Right on the, it's exactly 300. Paying for batteries. Batteries are super expensive unless they're rechargeable. You recharge them again, and that goes down to 150. You recharge them a third time, 75. Another time, 32.5. Every time you recharge them, that number goes down. But if they're a battery that you're just throwing away, super, super expensive compared to if I were to just plug it into the wall. If I would just plug it into the wall, it would cost me 12.6 cents per kilowatt hour. You're paying like 100 times more using a battery. And that's part B. Part B said, what if I just plugged it in and I used it for that same 100 hours? I paid $1.89 to make it work. Now if I plugged it in, how much would it cost? Part B. I'm looking for how much does it cost? So I want to end up with dollars. I'm going to get rid of this. So I'm starting out with a rate. $0.15 per kilowatt hour. So what I want to do is I want to strip away the kilowatt. So I'm going to put that on the top. And I also want to strip away the hour so that this cancels this, hours cancels that, and I'm left with dollars. So again, I remember from my previous problem, it was 0.00063 kilowatts. And we're working it for 100 hours. Multiply all these things together, and you get 0.000945. So, my headphones, it's like almost 1/10 of a penny to run them for 100 hours, or I could spend 100 times more and put a battery in. The moral of the story is this. Batteries are very expensive when it comes to per kilowatt hour. It's a lot cheaper for the power company. They make it in bulk, and they broadcast that in our power lines at very high voltages, so there's very little what's called line loss. And speaking of line loss and wires going in your house, there's a few things that I wanted to show you. Number one, I kind of mentioned it before, but I want to make sure that we get these down kind of officially. A fuse. A fuse is just a very small piece of wire that if you run enough current through it, it will break. So this is an automotive fuse right here, and you can see the wire inside of there. This is like an electrical component fuse, or house fuses. They, gosh, I don't see any house fuses. But you saw them in the previous video where you turn that plug in. A fuse It's a small piece of metal that melts if too much current. They're not so convenient, because if it melts, you have to replace it with a new one, and every time it does melt, you have to buy a new one. A much better option these days is a circuit breaker. Down in your basement, you probably have this panel. Looks like this. All of your rooms will be labeled over here, and you can look on the circuit breaker itself, and it will tell you how many amps on the switch there. It'll say 20 amps, so that this thing can take 20 amps of current before it automatically flips. You can go down, and then you can flip it back on. So you'll see here, talks of this one here, receptacles, I don't know, range and hood. So this is a stove. A circuit breaker, it opens if too much current. It protects your house, because if too much current flows through the wires, they're going to melt, and it's going to cause a fire in your walls. So these two things, they do the exact same thing. Fuses and circuit breakers protect your house. That's the important part. They are not protecting you. Things can still kill you, but this is going to protect your house and keep it from burning down. Now, this next thing, this protects you, a ground fault circuit interrupter. You've maybe seen these anytime you look at an outlet near water. So, meaning in your bathroom and in your kitchen. You'll see outlets that have these two little buttons right here. This protects the user. What it's doing is, whenever you plug anything in, electricity is flowing out, and then electricity is going through your device and flowing back in. If you were to become electrocuted, not as much electricity flows back as came in, and there's an imbalance, and this thing quickly turns the current off to protect you. So a GFCI it's building code to have, anytime you have water, like a pool, you have to have a GFCI outlet, and this is a GFCI outlet here. Protects the person. So you can test it. Push the button and it will test itself, and you can hit reset if it ever does that. The last one is this is kind of new. It's called an arc fault circuit breaker. And they look like this. They look like a regular circuit breaker if you go down into your basement, but they have this one little pigtail right here. So you'd see it down in a basement in a panel, and there would be an arc fault circuit breaker. They're a special type of circuit breaker that, if there's a very slow arc, like not enough to trip the breaker, but enough to cause a flash to maybe start a fire, this can detect that. I'm going to put in quotes, slow leaks.